17B. This is standard error. And remember that the standard error formula is the square root of the draws times the standard deviation of the box. So we have a 7-sided dice. We have 7 numbers in the box, and we are going to make 100 draws. How much would we expect to get with 100 draws? Well, the average is going to be, what's the middle number? 4. So if you add them all up and divide by 7, you end up with 4. So 4 is the average of the box. If I make 100 draws, I would expect 400 as my value. Okay. How would we calculate the standard error? Standard error is the square root of the number of draws times the SD of the box. So it's going to be 10 times the SD. To find the SD, I need to go into my list and put the box in. And then do one variable statistics. And I get 2.16. What does 2.16 tell me about the box? So the numbers in the box are 2.16 units away from 4 on average. Okay, but I don't multiply that by 100 because the percent error actually goes down. So I multiply it by the square root of 100, which is 10. 10 times 2.16 is 21.6. So 68% of the people playing this game will be within 21.6 of 400, which is a pretty small chance or percent error. And if we played more times, then the percent error would go down. Okay, so the sum of the draws will be around 400, give or take 21.6 points. Suppose you had to guess what the sum was going to be. What would you guess? 400. How much would you expect to be off by? 20. Okay, 400 is the best option, but we'll probably be off by around 20. Okay. 2. You gamble 100 times on the toss of a coin. If it lands head, you win $1. If it lands tail, you lose $1. The net gained will be around 0. We don't even need to do any calculations. It's going to be 0 because it's a fair coin. Give or take how many? Well, what's in the box? Now, how do I take the average of H and T? -1 and +1, because we need the box to have a sum of 0. So 1 and -1. Okay, so the average of the box is 0, but the SD of the box is going to be, how far off are they from 0? Yeah, 0 divided by 2, but it's still 0. So let's try it. Let's go into this, and I'm going to clear my list out, and I'm going to put 1 and -1, and then run my stat, and I get 1. How did I know it was going to be 1? Because I did know. On average, how far away are those numbers from 0? They're both 1 unit away from 0, so the average of 1 and 1 is 1. Okay, so for every draw, we would expect to be off by 1. If we play 100 times, it would be the square root of 100 times the SD of the box, which is 10. So my expected value after 100 draws is $0. But 68% of the people will be between 10 and -10. Okay? Now that's quite a big difference, right? But the more times we play, the closer we would expect to be percentage-wise. So let's say we played 10,000 times. What's the expected value? 0. The expected value is still 0. But then it would be the square root of 10,000 times 1, which would be $100. So this, in absolute terms, is closer to 0. But in percentage terms, it's much, much larger. Okay? This is larger in absolute terms, but in percentage terms, it's much, much smaller. I would play this game if you were allowed to increase your bets, right? You bet $1, you lose, you bet 2. You lose, you bet 4. You lose, you bet 8. And then if you continue that, when you win, for that set of bets, you will be $1 ahead. And then if you win, you keep betting $1. Now that's a really good idea, provided you bring enough cash with you, right? Because if you lose 9 times in a row, 2 to the 9th is a large number. Well, it'd be 2 to the 8th. 2 to the 8th is a large number, and if you don't have that much money, then you've lost everything up to that point. How likely are you to get 8 in a row? Not very likely, but it could happen. So as long as you bring enough cash with you, you can win $1 at a time, which might not be worth it. You bring $7,000 with you and you play for an hour and you made 25 bucks. Right? It's kind of sketchy. Okay. Where are we? 2? 3. Oh, give or take $10 or so, right? Your net gain will be around 0, give or take $10. 3. The expected value for a sum of 50 with an SE of 5. The chance process generating the sum is repeated 10 times. Which is the sequence of observed values? So expected value 50, what does that mean? That is what we would expect to happen, give or take 5. Meaning 68% of the games should be between 45 and 55. So when we look at this list, there's a 57. There's a not all of them. So we need to look for a list that has, and there are 10 items in the list. So we would expect how many of them to be between 45 and 55? Probably 7. Right? 68%. So it's closer to 7 than 8. So how many of are in 1 are outside of that? 1, 2, 3, 4. Right? Are there 4 outside? Okay, and the second one, 5. So 57, 57, that's 2, 61, that's 3, 41, oh, 58, 5. Okay, so the first one was off by 5. The second one has none. Right? In number 2, all of them are within 5. So the next one, yeah, that's weird. Which is the sequence of observed values? So in 2, they're all within, right? Yeah. And in 1, ow, that's a bad problem. What does the back say? 1? It says 1, but I mean, 5 were right and 5 were wrong. Okay, that could happen. In the other one, they were all right. So which is closer? 5 right or all right? Well, which one's closer to 6.68? 0.5 is closer than 1. So 1. Yeah. Now, is it strange that it didn't happen exactly as we wanted it to? No. Okay. So I would pick 1. Well, the back of the book picked 1. We certainly wouldn't expect them all to be within that. But 5 was a little high, which is okay. I mean, it's never going to be perfect. 50 draws are made at random with replacement from the box 1 through 5. The sum of the draws turns out to be 157. The expected value for the sum is, what's the average of the box? 3. 1 plus 2 plus 3 plus 4 plus 5 divided by 5 is 3. And we're making 50 draws. So the expected value should be 3 times 50, which is 150. The observed value is 157. The chance error is 7. How far off was the observed value from the expected value? 7. Do we care about plus or minus? Not really. And the standard error is, it's going to be the square root of 50 times the SD of the box. So I need to find the SD of the box. And then do my one variable statistics, and I get 1.4. So we're going to take 1.41 times the square root of 50, and we get 9.97. Got it? 5. Tickets are drawn at random with replacement from a box of numbered tickets. The sum of 25 draws has expected value equal to 50, and the SE is 10. Ooh, that's pretty high, right? If possible, find the expected value and SE for the sum of 100 draws, or do you need more information? So we have a box. We don't know what's in there. Okay? But we know that for 25 draws, the expected value is 50, and the standard, or the SE, which is standard error, is 10. Okay? So this right here is the average of the box times the number of draws. And this number right here is the square root of the draws times the SD of the box. If I double my draws from, no, not double, we are going to quadruple. If I change this to 100, I multiplied by 4. Can we calculate the new SE? What happened to my draws? I multiplied them by 4. So what will happen to the expected value? So if I draw 4 times more, what's going to happen to this number? Times that by 4. Does it ask for expected value? If possible, find the expected value. Okay. So the new expected value is going to be 200. Okay. What about the standard error? Square root the increase, right? You times your draws by 4, and the square root of 4 is 2, so the standard error will double. So the answer will be 20. So it's 220. All right, 100 draws will be made from 0, 2, 3, 4, 6. 0, 2, 3, 4, 6. True or false? The expected value for the sum of draws is 300. Well, average of the box, that's 5, 9, 15. 15 divided by 5 is 3. So 3 per draw. 100 draws would give us 300, true. The expected value for the sum of the draws is 30, or 300, give or take 20 or so. Well, I need to do my list. 0, 2, 3, 4, and 6. Oh, let me go back. Variable statistics. And I get 2.3. That's the SD of the box. I need to multiply that by, not 100, the square root of 100, which is 10, give or take 23 or so. Yeah. We'll be off by 20 or 23. Does it say false? So 23? Okay. We got, yeah. Okay, so it should be off by 23 or so. C, the sum of the draws will be 300. False. The sum of the draws will be around 300. Oh, so B is 300, give or take. And then D is around 300, give or take 20 or so. Yeah, okay. That's it. Can you see that you can't really hold to that standard error and say absolutely. Oh, really? So they rounded the 23 to 20 and said, that's close enough. Right? You're never going to be perfect. Okay, 7. In the simulation for table 1, if the computer kept on running, do you think it would eventually generate a sum of more than 3 SEs away from the expected value? We're not even going to look at it. The answer is yes. Why? Without even looking at the problem, how do I know the answer is yes? Because the SE works exactly the same way as the SD. If we go back to SD, if we do plus 3 SD, we'll be over here, and minus 3 SD will be over there. What is in the middle? This is 99.7. So if I were to run the simulation 1,000 times, I would expect to be outside 3 SDs how often? 3 times. If I ran it 1,000 times, I would expect to be off 3 times. So if we run it many, 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 many times, yes, we will be outside 3 SEs. All right, we're done.